The Arduino has been very successful at putting embedded computing in the hands of users. So I want to talk a few minutes about context and just get you oriented on the Arduino. First, what is it? Here's a shot of the Arduino website. The Arduino is a couple things. It's this little circuit board, which has a microcontroller on it that can interface to hardware. It's a store and foundation that promotes the idea and software. It's also kind of an open source movement that the design is open source. And there are many copies. In fact, actually, the board we're going to use in class is one of these. This is a basically Arduino clone made from the open source designs by Elegoo, which we buy in quantity for a lesser price, and it's otherwise equal to the Arduino. So what it really is, I mean, the Arduino came out in about 2005 as a small embedded computing platform, came out of Italy. And at the time, it wasn't an innovation in terms of capability or technology. It used a contemporary microcontroller of the time, but the real innovation was ease of use. It was packaged on a board that was very accessible. It came with a integrated development environment with tools for very easily getting your program running on the board, and a carefully selected language, which was beginner friendly and made it easier to start programming. At the time, there were many other microprocessor components you could buy, but typically it was much more work to get code onto them involving setting up compiler chains and elaborate tools or professional level tools. Things like the basic stamp were very proprietary and quite closed. So the innovation was as much kind of an open platform around kind of beginner friendly principles. And in some sense, it's a little bit of a victim of its own success. Here it is. It's 15 years later and we're still using it. It's quite a small, simple platform. But the same token, there's a ton of resources online. There's user communities, lots and lots of sample code and tutorials that have been written around this that make it a very easy starting point, even as the hardware itself is, in some sense, quite primitive. It has spawned a lot of clones, both in terms of the specific boards, as also like more advanced boards that operate on the same IDE. And in some sense, that is really the secret now, is that the same programming system and the same sort of philosophy of how to write the programming language and tools has now been expanded to include many other boards, often much faster and bigger ones, but that still sort of hew to the same general design style of the Arduino and are also equally user-friendly. Couple commercial ones to note, there's the Teensy, which has got a ARM chip on it that's a 32-bit chip that's much faster. There's also like the Node MCU, like the ESP8266 ones. The number doesn't matter. What matters is that they're very internet-friendly. They're a very popular chip that can get on a Wi-Fi network and put embedded hardware onto the internet. And then the other thing is that there's ways of making add-on boards called shields that plug on top of these boards that extend the functionality. And there's hundreds of those in the market that are a kind of one-stop way of adding hardware onto an Arduino. We're instead going to build up circuits on breadboards and kind of start from just the raw platform instead of using shields. But just it's good to know all this stuff is out there to be available. Now, we're going to just sort of talk a little about kind of the specs of the thing. As computing goes, it's pretty primitive. It's an 8-bit microcontroller. It has a 16 megahertz clock, which is a tiny fraction of your typical like 2 to 4 gigahertz, computer clock these days. 2 kilobytes of RAM, such a tiny amount of memory compared to, literally a typical desktop has, sort of 8 to 16 gigabytes now. That's literally millions of times more. 32 kilobytes of flash for program storage. Again, a very small program store for very small programs. And then it has analog inputs and outputs. And I think that's the key, is that the physical pins here allow one to easily just plug wires into it that gets access to like low-level digital I/O. This is an Arduino Uno. The sort of slightly larger cousin of it is the Mega, which is a similar 8-bit microcontroller, but has slightly better specs. But even then, it raises the ROM to 256K and the RAM by a factor of 4 to 8K. It's still quite a sort of small computing device. So our use for it really is as an I/O device. The real win on the Arduino is that access to hardware is almost trivially easy. You can plug a wire into a socket and have a connection. The number of layers of software to like manipulate that hardware is very small and simple. So your programs run very close to the hardware. You can manipulate digital wire signals at very high rates because even though the overall computational rates are low, the amount of overhead to accomplish things in the digital world is also very, very low. So they're good for kind of low latency control of sort of simple projects. Where they're not so good for is things that require a lot of computation or especially a lot of memory. So it's possible to do some audio projects on an Arduino if you're clever, although it's tricky without that much memory. all integer computation, all using sort of just no memory. Video is equally very difficult, although people have created video signals with Arduinos before, but it's very difficult. I think the big secret for us is if we need more computation, we have access to it across the serial port. There's a USB port that can plug into a host computer, and with adding that connection to the host, we can then send data back and forth to a host computer and access kind of arbitrary level amount of computing and other resources. The downside, of course, is it's communicating at fairly low rates across a serial port over USB, so the limitation ends up being the latency of getting data on and off the Arduino. That said, the hardware is quite capable. There are hobby-grade CNC machines that are run entirely by an Arduino, including generating paths and curves and controlling accelerations and decelerations of the hardware. With good programming, that computation can be really stretched to do quite a bit. The limitation being those CNC machines are also depending upon a host computer sending down the files as they cut because they have not enough memory to actually store much. So using the Arduino involves a kind of careful attention to like choosing exactly the right kind of problem to solve with it. But for our purposes, controlling simple motor-driven and hobby servo-driven mechanisms with sort of low bandwidth input from like switches and single point sensors, there's more than enough computation to use. And as a kind of sequencer controller, it ends up still being a very, very useful platform. We will program the Arduino board using a special dialect of C++. I'll now give you a high-level overview of the language. This is oriented towards students who have some programming experience, but not necessarily Arduino experience. As a starting point, I'm going to show you the web page, which is the language reference. This can be found from the help menu inside the IDE or on the arduino.cc website. And what you'll see is that some of the keywords are familiar. They're basically C++, largely also C keywords. But then there's some special keywords and constructs that are very Arduino specific. It's a specially chosen subset of C++. It's designed to avoid a lot of the complexities of C++, but still provide kind of beginner-friendly programming in a syntax that is C. For our purposes, we'll basically treat it as C and not get too concerned, although it's possible to use more advanced C++ features. In practice, programs are compiled, downloaded, and run, and there's a whole cycle to getting a program to go. For our purposes, we're going to be using Tinkercad to do the demo at first, and so it's just simpler. There's no separate download step. We're primarily going to be doing numerical and logical computation, so dealing in numbers and true-false values. So the most common kinds of data we'll use will be Booleans, small 16-bit integers, larger 32-bit integers, and sometimes floating point numbers. The Arduino can do floating point. It's not terribly fast, but that can also be useful. We'll also use data tables like arrays and maybe occasionally strings, although most string processing isn't that useful for us, and it also burns through memory very quickly, so the capabilities are kind of limited. I brought up here a kind of sample circuit and sample program. It has a hobby servo connected to an Arduino and an oscilloscope to show the control signal. If I run it, you can see that the Arduino emits a variable pulse that you see on the oscilloscope, which is commanding the hobby servo to move back and forth at a regular rate. So just looking at the program briefly, and this uses some various features we'll break down separately at other times. It is C++. It's a text-based language. It's line-oriented with lines that are terminated. There's functions that are declared. There's variables that are declared both outside, globals outside the functions, as well as inside the functions. So let's just walk through a couple of features just so we kind of see what's going on. The first is this example actually does use C++ objects right off the bat. If you look at the top, there's a servo object that is called indicator, which is a complex data object that's designed to represent the physical connection to the hobby servo. And this is the first example of a case where it is declaring a C++ object, but the syntax is quite friendly, and one can simply ignore the C++ features and treat indicator as a data object to manipulate. In this example, there's two functions, and this is characteristic of the Arduino system. There's a void setup function, which is a function that's called once when the chip initializes, and in physical world when it powers on, which is used to set up initial state, initialize hardware, any kind of one-time program activity. The second function is called loop. inside the firmware, this function is called just repeatedly inside a while loop. And the idea is that most embedded programs have some kind of operation cycle that they repeat infinitely as long as power is applied. So the loop function is called again and again just to perform actions. In this case, what it's doing is it's keeping track of how many times it's run with a step counter. It's using a little bit of math to calculate an angle from that, the math library sine function to compute a varying signal, and then line 22 here, the indicator.write. It's taking some computed angle in degrees and sending it out to the hobby servo. And there we see once again that notation of indicators.write is a C++ method call that uses some other library logic to send a signal to the hobby servo. And then the delay is meant for regulating the speed. It delays 50 milliseconds, so this loop runs 20 times per second. A couple things to note. The nature of an embedded system is that it's very hard to debug. There's signals that are generated electrically, and otherwise there's not a debugger built in to stop and check state. Sometimes it's very hard to tell what's going on. Two features that help with that are that there is a serial monitor, which in this case is just a window, but in the Arduino would be a window within the IDE. And that prints out data that comes back over the serial port from the Arduino. You notice that there's a line in the program, which is the serial print line angle, and an initialization, serial.begin. These are used inside the sketch to initialize this connection to a serial port, and then allows one to send data back up the serial port to the host. Another feature here that we can use is that the Arduino IDE and this interface both include a plotting function, which if given a series of numbers will just produce a graph of the data. These are features that make it much easier to debug basic programs and see what's happening, to send data back and visualize it. All from a platform where it's otherwise kind of invisible to see what's going on. So those are some essential features that kind of show basic C++ structure of functions, variables, some control flows, some Arduino specific features like the specific step and loop as entry points, the servo as an object that can drive hardware, the serial port as an object that can send data back up to a host. We're going to use the Arduino as an embedded computing device, so our emphasis will be on interfacing to the physical world. That interfacing does require special input-output operations, but also a fair amount of typical data manipulation and programming and logic. So in this video, I'll walk through some essential programming vocabulary in the context of the Arduino. This will assume some minimal programming exposure, but no special Arduino experience. So the basic workflow here is we're going to build up a sample program step by step and talk through a lot of the elements as a way of getting oriented. So I have a Tinkercad sketch open. It has just an Arduino and no I/O because we're going to be doing purely computational ideas. So the way we start out our programs is with a setup function. So let's go through this bit by bit just to see what's happening. A function in programming represents an operation that takes parameters, executes some computation, has some side effects where things happen, and then returns a value. In this particular case, there are no arguments and there's no return value. So it's only about providing a point for control flow for the side effects. So in this case, the setup is the name of the function. The parentheses, I undid that. The parentheses afterward would normally contain the argument list, but in this case it's empty. And void is a C++ keyword that means doesn't return a value. The braces are essential. The braces define a block in C++ language, which is the body of the function. And inside that block can be other subblocks, but all the lines that constitute the body that will execute when the function is invoked. In this case, we're using one method call to the serial object. This is a predefined Arduino object, which is a representation of the USB serial port. And by calling begin, we're calling the Arduino system to initialize the serial port hardware and the internal software with a given baud rate. The number is actually a communications rate in bits per second. It has to have certain particular values. I'm using here 115200, which is one of the fastest reliable rates and what I just always use in these sketches. And that determines how fast data will flow between the Arduino chip and the USB chip and has something to do with how much data we can get back from the Arduino. So that sort of sets up the one function call there. let's go ahead and do one more thing, which is to declare a global variable. This is a C++ variable declaration for the variable count. It has type int, which is a predefined integer type, and it gives it a value of 32,700. The Arduino is an 8-bit chip, so that native integer types are only 16 bits, and so thus they have a fairly low range of values. The maximum positive value is 32,767, and about roughly a symmetric negative value. This can sometimes come to be a real problem in programming if you need to count or manipulate larger values. So for those, we would use a different long integer type. But the native type is an integer, and it's a very useful type for all sorts of sort of basic iteration and constructs. Next, we'll go ahead and introduce a loop function. And now we have at least a complete program. Again, loop is a predefined entry point that the Arduino system calls. It has, like the setup function, it's given no arguments and it has no return type. So it's basically an entry point for calculation or for computation to proceed into. And inside the Arduino firmware, there's a while loop that simply calls this again and again and again and again. Whenever it executes, it's simply re-invoked. And it provides encapsulates this idea that most real-time systems have some essential computation loop that's run endlessly, and that's kind of the basic cycle. You don't have to let it exit. It's possible to have Arduino programs that just enter loop and then act within it, and that's also perfectly legitimate. So once again, we see an open brace and a closed brace to define the block of the body, of the loop function. And there's 3 lines. The first is count equals count plus 1. Remember, count is our global counter variable that exists outside the function. Because it was declared globally, it is initialized with its initial value before your program begins executing, and then it will retain the memory of changes as the program proceeds. So this count equals count plus 1 will increment the count value. It'll read it, add 1 to it, and store it back in the same location. Serial.println is a operator in the serial object which will print a value, and it can take a lot of different kinds of data and will apply the right printing logic. The key is that it's a very straightforward system where you can only print one value at a time. So println is a shorthand for print and add a line feed to end the text line. So often if you're creating a lot of complex output, you have a series of print functions that end with this print line. In this case, we'll pass it a single integer and it will print the value out. And the delay of 100 to delay, so the loop runs approximately 10 times per second. And then the loop will exit. And in the bottom, I've opened the serial monitor. It's sort of the bottom area of the window down here, serial monitor, which will show us the data that comes back. So if I start the program, we'll see it start to count up. It's counting values, these integer values. And if we wait a few seconds, we'll see it get to the end and hit the max. There we go. We rolled over. The Arduino, like a lot of these chips, uses 2's complement arithmetic, technical term. But the thing to note here is when we went beyond the maximum positive value, the chip silently wrapped around to the maximum negative value and then started counting up from the maximum negative value. That's on the Arduino, that sort of mathematical overflow doesn't create any kind of exception or other error. It just silently wraps around and then continues executing. And this is a case where the outcome is harmless and expected, but sometimes that can lead to sort of unexpected logic in your programs, and it's something to be aware of. Also down in the Arduino, in the simulated Arduino IDE here, the Tinkercad IDE, is a graph button that will show a plot of numbers that it gets on the serial port. It's reading the text value that as if you would read it back from the serial port, and then dynamically creating a plot to show you the kinds of values that it's seeing. If I stop and restart the simulation, we'll see that initial climb as it gets to the maximum positive value, and then cycles around to the maximum negative value. And there we see that there's a kind of a weird step function. So this is a basic execution flow using the Arduino loop function as a kind of means for looping. Let's step back a bit and talk about just some very essential control flow operators that we might need in other cases. First, we're going to add a little logic into the middle of this function here. Going to add an if statement. And this will give us a few more things to talk about. And then I'm going to set it running. So while that's running, we can discuss this. The statement is if, and then there's a set of parentheses, count equals 32767. And then there's another close parentheses, and then another set of braces that encapsulate another block. The basic structure of this is it's an if statement where it's if, and then there's an expression that has some true or false value, and then there's another block that is executed. For our purposes, it's always good practice to use the braces and have an entire block, although that block might consist of a single line in some cases. Now we see this kind of sawtooth pattern emerging on the oscilloscope here, and see that the values in the monitor climb to the maximum and then cycle back. So what the if then is doing is if it detects that the count has reached the maximum integer value, it then, the predicate evaluates to true, and then the control flow will enter the block, that's the braces, and perform this assignment operation of resetting the count value back to this 32,700. And so this is a way of executing a slight variation in the logic where the value climbs to the maximum and then is reset before it rolls over. It's still using the essential Arduino loop structure that it allows loop to exit and then re-enter as if it were kind of running a whole programmatic cycle. And the reason that works here is because the count value is a global variable. It's defined outside of the function, and so it retains memory of its value all the time, even as functions exit and are re-entered. Now this is also a useful structure just to have a way to create some logic in the form of an if-then. Now we're going to take that out and use the loop function in a slightly different way. So I'm going to shift examples here to introduce a while loop. And to spare the type, I'm going to kind of paste it in here. But now we can see a slightly different logic. So let's read through this new little bit of code. So if we look inside the loop value now, there's a sub loop inside of the loop function. And the format here is the while keyword, and then an expression, which is a predicate that can evaluate to true or false, followed by a block defined by the braces. In this case, the brace has the 3 lines within it. So the logic of this is, while count is less than some value, in this case the maximum value, while that evaluates to true, then the Arduino will enter and execute the code inside the block. So as long as the value is within range, less than 32,767, it will increment count by 1, print the value, and do the delay. Since count is now incrementing again, it will climb up 1 by 1 to the maximum value, and eventually the while will then evaluate to false. The count will be equal to 32,767, and then it won't execute the block. Instead, it'll go past to the next line of code, which is line 5, which resets count to 32,700. At that point, loop function will exit, and then immediately be re-entered, and this will all happen again. So if we start that, we should see similar behavior. The serial monitor is counting up, and the plot is climbing, and this is now within the while loop. And then when it gets to the end, it resets count, the loop function exits, and then re-enters. So now the loop function is actually running much less often. It's only running once for the entire cycle of the waveform, and the while is what is regulating the count up 1 by 1. That's a very common structure to have, a kind of conditional loop where there's some kind of variable that's changing in the middle. So there's a very convenient shorthand for that, which is a for loop. And that's what we'll look at right now. So I'm now once again sort of excise the body here of my loop function and insert a slightly different structure. We're still using the same count value, and we're still getting essentially the same behavior. We're getting a count that goes up to the limit and then cycles back down to the initial value. And the program dynamics are very similar. Loop is entered, some waveform is generated until it's done, and then it's exited, and then loop re-enters and does the next cycle. In this case, though, we're using a very common structure, which is a for loop. And it doesn't actually add any additional capability over the previous example using the while loop, but it is a very convenient syntax and shorthand for sort of writing the same ideas in a more compact way. So what we see here is there's a for and then an expression with 3 terms. Count equals 32,700, and then a semicolon, and then a second term, which is a conditional, again, count less than some value, and then a third term, which is an expression with an assignment. It has that same increment, count equals count plus 1. After that triplet of expressions is a block defined by braces, the curly braces, and inside that is the print line and delay. So the three terms of the count are always an initializer that is acted on once, that in this case assigns a value to count. The second term is a predicate, and as long as that predicate is true, then the for will continue to run. And then the third is a update expression that is executed right before the loop resumes. And then the body is executed sort of once per cycle. So this is a very conventional form where the basically it's used as an incrementing counter to go up by 1. But there are many other ways that the for structure can be used. And in all these cases, it's an initializer, a predicate, and then some kind of expression assignment or some kind of evaluated expression that happens once per cycle. Any one of the three can be omitted. Sometimes you'll see just a blank space and a semicolon, and then that's simply that part of the for structure is not actually used. So just in the synopsis, we've looked at the essential we've looked at the essential C syntax for some function declarations that in this case don't take arguments but do provide entry points for control flow. Talked a little about control flow through setup and loop. Talked a little about sort of globals, assignment, if-then structures, while loops, and for loops. And these are all essential idioms that we'll use a lot in our programming. Many of our Arduino inputs and outputs will be digital in the sense that they have only discrete states. So for example, switches and LEDs are either on or off, and we can treat them as binary ones and zeros. In this video, we'll discuss the essential digital input and output operations that we can do with these signals. Before we begin, let's just sort of discuss the meaning of a single bit. It's context sensitive. It depends upon the semantics of where it's coming from. So just to make an example, if you had some sensor at the middle of something like a nuclear reactor that was detecting whether it was going to melt down or not, that 1 might be very informative. It might mostly be 0, and then a 1 is an emergency. And the 1 by itself doesn't carry that. It's the context of where it's being interpreted from. Likewise, digital signals that might be on or off can also vary in time. And we often use that to encode data numerically. The signals that come across your network are effectively binary at some level, but then encode numbers and data, but can also be essentially analog. A pulse that varies in width in some analog way might encode an analog value as a variation in the timing. So the digital signals can be used in lots of different ways, but we're going to start with sort of simple on-off kinds of signals. So to see the example here, we're going to look at a circuit that has 1-bit input and 1-bit output. Tinkercad set up with a breadboard with a switch with a pull-up resistor and an LED with positive logic driven off an output that are wired to our simulated Arduino. That'll give us something to look at. So to delve into the code, I'll open the code window. And let's just walk through again, kind of line by line. And there's a few C++ things we'll talk about on the way. The first is I've made some definitions that describe my hardware. The very first couple of lines here, const int a name, which is switch underscore pin, and the value 8. This is a good convention. I basically defined a compiler constant. The const says it's a constant value that'll never change. I've given it an all caps name, which is just a convention for a constant value. It's not essential, but it's a good convention. And then the 8, which in this case describes a pin number. And on the circuit, that is the digital pin 8 on the upper row of pins there. The second is LED pin equals 4, also defining that the LED is wired to the digital output 4. We'll use those in a second here. Inside the setup function, we see a new function, pin mode, with a capital M on mode. The first argument to pin mode is a pin number, reflecting something in the hardware. And the second is a keyword output. The Arduino has a set of digital inputs and outputs, which are pretty configurable. Even the analog inputs can be used as digital mode inputs and outputs. So when you start your program, it's important to tell the Arduino the nature of the hardware that we're going to be using, specifically by what mode to run each pin in. So in this case, we're declaring that the LED pin will be an output pin. Otherwise, it would default to an input, and the output operations wouldn't even work. The second mode there, pin mode switch pin input, effectively redeclares the default to say that it's input, but I also consider it good programming practice to explicitly label the function for each pin so that when we read programs, we understand what we're trying to do. The input and output are Arduino-specific keywords. They're not part of C itself, and the pin mode function is part of the Arduino API. So there we start up and we tell the Arduino, use this pin for output, use the other pin for input. In the loop function, we basically transfer data around. We see a new function here, digital read, which is given a pin number and performs some operations to go to the hardware and sample the value as a digital input and return a binary value. So physically, there's a voltage on a pin that can occupy some range of voltages. The hardware itself discretizes that, so that voltages below some threshold get read as a digital 0, and voltages above some threshold get read as a digital 1. So in our case, it's a direct translation from voltage to a value. And then that returns a value. Now we're seeing a function call that takes a parameter, returns a value, and returns a value that we store into this variable that we call value. Note that value is declared within the function. Technically, it's an automatic variable. But the key is, because it's declared in the body of the function, it can acquire values and be used for calculations, but then effectively vanishes when the function exits. So it only has a value while the body of loop is executing. We print the value to see it, and then we call the digital write function. Digital write takes two arguments, a hardware pin indicator, in this case the LED pin number, and then a logic value to send out. So in this case, it'll be either 0 or 1. And then there's a delay just to slow the overall execution. So when I run this program, I'll hit start here. Let me make the LED more visible. There we go. The LED is starting at, I apologize for the manipulation here. I'll get that there. Okay, there we go. So the LED is starting visible, is glowing. And the reason is that the fact that we used a pull-up resistor. So the switch is currently open. The digital input is actually defaulting to the 5-volt input, and that's being read as a 1 into value, which is then being written out to the LED being on. If I press on the switch, we'll see the LED goes off. Maybe we'll zoom in on that. Here we go. LED goes off. So when I press on it, then the switch closes, brings the voltage down to close to 0 volts. That's discretized to a digital 0 as a value, and then that is output to the LED as a low current, which then the LED is off. So the key to emphasize there is there's a physical voltage, there's kind of some kind of signal. There's hardware that's transducing that to a 1-bit value. And then the digital read and digital write functions are used to sample that value and return what's a number, which at that point is a digital 0 or digital 1. I mean, the nature of computing is there is no ambiguity at that point. A 0 is a 0, a 1 is a 1. Any kind of ambiguity in the voltage, any kind of noise has been eliminated to a definitive value. The other thing to note here is we're going to start to see more of this. It's not read continuously. There's a cycle where it's sampled, processed, and then there's some delay. And even if we took the delay statement out, there's always some processing time. So any kind of change in the input doesn't necessarily have an immediate effect here. The program has to actually sample that value and then act on it by producing another value on the output for any change to occur. And that cycle time is another property of digital systems that happens over time. Just to close here, I'm going to jump over to the reference for one moment. One thing you may need to do in various assignments is to generate audio. And there is a built-in function called tone. It is possible on a real Arduino to simply cycle the output on and off fast enough using digital write to create audible rates. So frequencies that would then generate sound and run through some kind of speaker. The hardware has some special hooks, some actual hardware support for doing this more efficiently. So the tone function is provided as a way of generating a square wave on an output that can produce an audible pitch. And if we look at the syntax, there's a couple modes. The most common is simply the first argument is a pin number for where the output's going, and the second is a frequency in hertz for the tone to produce. And that's a way that will produce melodies and produce audible pitches. I'm not going to demonstrate it in Tinkercad, but that's actually the right path to go. So just in synopsis here, we addressed very briefly the kind of semantics of what digital might mean, emphasize the fact that like physical voltages get turned into numbers, and then numbers get turned back into currents and voltages through these operators. And then the syntax being there's these two functions, digital write and digital read, which you'll use quite a bit as the essential operations for input and output on a digital level. The physical world is an analog place. The processes that we can see take place with a continuum of states. So when we measure the world, we may end up using some sensor, an analog transducer, which takes that physical process and converts it to a varying voltage. So when we use the Arduino, we have to think, how can we convert that into some computational quantity? Likewise, motors are not simply on or off. They can run with different currents and different rates. So we'll look at the Arduino capacity for this analog input and output. I'm going to introduce a Tinkercad sketch, which has just some analog input. At the bottom is a potentiometer wired between +5 and ground. And now the input is going to A0, which is one of the analog inputs on the Arduino chip. I've also wired an oscilloscope up to one of the outputs to see how this program works. So just to sort of show it running, I'll just go ahead and start it. And what we see is, if you look in the serial monitor, there's some number being printed. As I move the knob of the potentiometer, that number is changing, and we get a graph of a varying signal. And also, the oscilloscope is showing some waveform. So let's back off and show this step by step. The first thing that's happening in our loop function is a new function, analog read with a capital R, which takes a pin number, in this case from a different category of labels. A0 is the analog 0 pin. What it does physically is it runs some piece of hardware inside the Arduino chip, which measures that voltage, takes a little time, and produces a number, which will return as an integer and store in this input variable. It's specifically a 10-bit converter. So it has 1024, that's 2 to the 10 power, of values, which range from 0 to 1023. And that maps to a range of voltages from 0 to 5 volts. So 0 volts produces 0, and 5 volts produces 1023, and it's proportional in between. We're printing that value out, and then we're also using this analog write function I'll come back to in a second. The first thing to know is it does take some time to do the conversion. If you actually run an Arduino at full rate, you'll see you get roughly 10,000 samples per second on a single pin. The multiple pins are multiplexed through a multiplexer circuit onto the same converter. So if you read multiple pins, that 10 kilohertz overall data rate is just divided by the number of inputs. The other thing is that it has limited precision. It's only 10 bits. It turns out that 1023 levels, discrete levels, is not bad for a lot of sensors, but it's still a lot less than other systems. So for example, audio systems are frequently 16 to 24 bits. So the signals are measured with a much higher resolution. The second question is about precision. The converter is relatively noisy. So if you're measuring a single value, a physical value, which might seem to have a constant voltage, it's not uncommon for the bottom bit or two of the analog converted value just to vary with noise, which represents a change of value, kind of +1 to +2, that's sort of randomly distributed. Better circuit practices can keep that down, but basically there's always some amount of noise in the red signal, which of course we don't see in Tinkercad. The other thing is that basically because we're sampling in time, this is a very low rate signal, so we can oversample it tremendously. But if your signal is varying quickly, then the sampling rate can definitely introduce artifacts and aliasing. And so this is only relatively good for fairly slow signals like these physical transducers, and not that applicable to audio. If you try to measure a microphone directly with an Arduino, it's just not possible to measure above roughly 5 kilohertz signals because of that 10 kilohertz sampling rate. And in practice, it's just very hard to measure audio directly using analog input. The second element here is this analog write, which isn't actually an analog output. If we go ahead and run this simulation again, what we see is I read the value of voltage on the potentiometer, and I get some number. And here I'm bringing the wiper up of the potentiometer up to the 5-volt rail to see the maximum value. And here I'm bringing it back down mid-range. What we see is on the analog write signal is producing a waveform on pin 3, which is not analog in the sense of varying in voltage, but it is analog in the sense of varying in time. So for a large value, the upper part of that pulse, the positive piece of the signal, is wider. And for lower values, the pulse width, the upper part of the signal, gets narrower. This is what we call pulse width modulation, or PWM. And it's a way of encoding an analog value in a digital signal. And it is quite useful. A couple ways to think of it is it's either encoding information in the sense that if one were to measure the pulse width, there is some variable value there that could be reinterpreted as a number. Another is if you're actually using a signal of this shape as a source of energy, then the average energy delivered is going to be related to the pulse width. So when we drive motors, typically we use some kind of pulse width modulated signal. So to run a motor at half speed, you typically create a square wave where the duty cycle or the on time is roughly 50% on, and then that pulse width will produce a lower average energy than if the motor were simply connected to power. It's also possible to build analog circuits that filter that down to a voltage if you truly need some variable voltage, but it has a built-in sampling rate. There's some cycle here that is actually fairly low. It's an audible rate, and so that governs how fast that analog voltage could change. So just to back up here, we have 6 channels of analog input on the Arduino. They're 10 bits, so there's 1024 possible levels of input. They're fast enough to measure all the physical processes we need, not so fast that you'll have an easy time measuring audio rates. They have a 0 to 5 volt input range. They produce an integer value, and then we can use those values throughout our computation as filtered, to create signals that we filter and modulate and process to do other kinds of decisions. In this case, we're just using it to generate a pulse width modulated output. It uses the confusing name of analog write as the output. Everything takes time. Physical processes do, computation does, humans do. So the measurement of time ends up being a central need in physical computing. We'll look now a little at the Arduino timing system. The Arduino doesn't have a real-time clock in the sense of a wall clock that measures hours and minutes. Instead, it has some hardware counters that measure elapsed time for when it turned on. So it's good at making relative time measurements, but doesn't know the absolute time or the calendar time. The clock hardware is driven by the system clock. There's a 16 megahertz crystal driving the Arduino itself. So the actual time resolution can be on the order of microseconds or tens of microseconds. With some software, the upper limit can be arbitrarily large. Even if the physical hardware rolls over, with clever software, you can keep track of that and measure arbitrarily long intervals as long as the chip can run. So a lot of the beginner code that we've seen uses delay statements as a way of regulating the flow of time by simply capturing execution for some interval. There's also a delay microseconds, which can do that to somewhat higher precision. But one question to ask is, what is happening during that delay? And the answer is really nothing. While the Arduino is in the delay statement, it's waiting for the hardware clock to roll over some amount, and then doesn't do anything useful. It just sits there in a tight loop. And so no other calculations can be performed. We'll see in the end that this is a somewhat limiting structure for the program, because very much we'd like the system to be doing other useful things while it's waiting. So by measuring time more directly, we have a means for controlling program flow and measuring time and regulating rates that doesn't involve the delay statement. But just to get started, let's look at an example and walk through the details. So I have here a Tinkercad sketch. There's an Arduino in the circuit, but we're not going to even use it because or any hardware. We're just looking at the internals of the Arduino. And I'm using a couple more functions here and a couple more data types. First is, inside the loop, there's a reference to the function micros, and it returns a long integer, which we're going to store into this variable called now. Micros is a function that reads the physical hardware, both a sort of like once every millisecond count, as well as the underlying hardware count, and returns a value with units of microseconds, which is the number of microseconds elapsed since either the Arduino started or the last time that the counter itself physically rolled over from its maximum. In the second line, we also use the function millis, which is short for milliseconds. And it is similar. It returns a value, which is the number of milliseconds elapsed since the start. It's also a long integer. It prints that out and prints a space. Then it prints out the current micros value and prints a space. And then the last thing it does here is it does a subtraction and prints the value, which is basically the timestamp now subtracted from the previous time that the loop ran, and that will tell us the elapsed time for the loop function. And then the last thing it does is there's a global variable last time, And the last thing the loop function does is save the new timestamp back in that value. So when we run this, and I'm going to open the serial monitor to see it, we'll see a couple columns of numbers come out. This is the case where we might see a distinctly different value on either your computer or on a physical Arduino as opposed to the Tinkercad simulation, just because the nature of timing in the simulation is much more dependent upon other factors and there's no Arduino hardware. So the first column is showing us a millisecond count since I started the program. That's from the millis function. The second column is showing us a microsecond count from when I started the program. That's the micros. And the third column is showing us the elapsed interval. And the units are microseconds. So we see there roughly 2,000 microseconds or 2 milliseconds. So this simulated Arduino is ticking over at a rate of about 500 times per second running the loop function. This is to say, I mean, honestly, I think that's actually, this rate is largely driven on a physical Arduino by the serial port. On the simulated Arduino, I'm not quite sure what is the rate limiting step. It turns out on a physical Arduino, the serial print operation is sending bytes at the serial port, and actually sending data at the serial port ends up being much slower than any other calculation in this loop. And so the overall rate is actually limited by the print functions. Without the print functions, this can run very fast. It's quite possible to run a loop function on an Arduino that runs on the order of hundreds of thousands of times per second, or even more, just because even though the underlying chip is not terribly fast, the amount of overhead in each of the operations is also quite low. It takes some time to get used to the relative timescales here. A microsecond is, from a human standpoint, an infinitesimally small time, and yet reasonably long on the scale of electronics. So part of working with physical systems is knowing kind of where to fall in these units. When we build physical hardware, of course, it's subject to physics rules and the physical behavior. And so very often the time constants of things happening in terms of macroscopic motion end up being tens and hundreds of milliseconds. But the Arduino is capable of measuring at much finer rates. So just to summarize, the Arduino has some clocks, a way of counting units that are related to the hardware clock at precise levels down to the order of microseconds, and then a slower clock that measures milliseconds from that. And then with software, you can measure longer intervals. We can both measure intervals by recording timestamps, as well as sort of control the execution rate by governing when code is executed based upon clocks. And a kind of hint that in the future, we're going to try to back away from using delay in terms of more specific calculations using the clock values as a way to regulate how fast things run. Here's a difficulty with the Arduino delay function. The chip can't do anything useful while it's waiting, and that includes processing inputs and responding to events. So let's look at a possible solution. We're going to look at the lecture sample code from the course site down at the responsive delay example within the event loop section. And I have it over here in a Tinkercad sketch, which includes a speaker on pin 5 and a push button switch wired to digital input 3. So let's first just observe what happens with this. And this time, if I click the switch, it truncates the sequence. It interrupts the siren. So let's look at how this is achieved. If we look in the body of the loop function, what we see is that play siren is called normally, and then after that it plays silence. So it seems clear that play siren is somehow ending early when the button is pressed. If we look down into play siren, what we see is there's a loop that will do the 3 cycles of the siren, playing a tone on the speaker and then another tone that's lower. And we have this new function, condelay, which is defined within this file. And the idea is it's a conditional delay. It'll delay for 300 milliseconds unless something else happens. And if that something else happens, then it will return true. So if the expression with the if is, if condelay returns true, then apply the return operator. And in this context, a return operator will simply return immediately from play_siren. So let's look inside of condelay. Condelay is a function that takes an integer number of milliseconds to wait and returns a Boolean, true or false. So basically what's happening inside here, there's a loop that is running as fast as possible, sampling the millisecond clock. Every time it runs, it reads the clock, sees how many milliseconds have elapsed since the last time it ran, and using that to keep track of elapsed time. And then that's effectively re-implementing delay. But the key is inside of that, there's an expression which also reads the switch. So in this case, we have an active low switch input. There's a pull-up resistor, so when it's pressed, it goes low. When that digital read of the switch equals 0, that means the switch has been pressed. What happens is then the con delay function will immediately return true as fast as possible, really within microseconds of the signal going high. And then going low. If the loop completes, if the full time elapses, then it'll return false to indicate that the full time elapsed and it returned normally. In that case, inside of the siren function, the loop will just execute to the end. There is a little subtlety to what's happening inside of the loop in con delay. The millis function returns a 32-bit unsigned integer based on the hardware clock, and that is the number of milliseconds elapsed since the chip was turned on. That can roll over. It takes about 50 days. That would be, the maximum value would be on the order of 4 billion, and 4 million seconds divided by 86,400 seconds a day ends up being about 50 days. So it's always worth handling that case correctly in case your Arduino program happens to run for a very long time. What we'll see here is that the interval calculation is keeping track of the previous read and doing a subtraction. And it turns out that in the 32-bit math, that handles the wraparound correctly. Even if the clock overlaps and goes from the maximum value back down to 0, the subtraction will always produce the number of milliseconds that has elapsed since the last time the loop ran. That is used then to compute a descending count of milliseconds. The other thing to note is that this loop can run many, many times without millis changing. The loop is running quite quickly. These operations are very fast, so millis might return the same value many times in a row. The value of interval will just be 0 in every case, and milliseconds simply won't count down. But in every case, the digital read is happening at the maximum possible rate for the lowest possible latency on the switch being pressed. Now, this is a very general sort of structure that can be extended. Inside this loop, there could be a lot of other actions that are all polled at very high rate, either to calculate some kind of output value, do some other kind of processing. It can turn your program inside out to include a lot of sort of real-time operations inside some kind of con delay structure. But this is a way, at least, of thinking more explicitly about the flow of time in your program, taking charge of the delay operation so that you can accomplish something useful while it's running. And that is sort of the very first example of what we might call event loop programming, where the idea is there is some loop inside the program that is simply processing events, and then as things occur, like time passing, then different actions are taken. I'm going to walk through some of the sample code from the course site to explain some details about tone production in the Arduino. Let's go to the site here. There's a section, Lecture Sample Code, that has a series of short sketches. And we're going to go to the sound section and look at the first example called tones. I'm just going to copy that text here. And I have in the other tab a Tinkercad sketch that has a Arduino with a piezo speaker attached via resistor to digital pin 5. So I'll paste that in, and then we'll give it a quick listen. And we hear a low pitch and a high pitch with a short silence in between them. There's some clicking. That's really an artifact of Tinkercad simulation and won't be exactly the same on a physical Arduino. So let's look at the code. It starts out with this constant speaker pin, which declares a name for the pin 5 so we can read the program. I do recommend using this kind of construction. And then we'll notice that the setup function is empty. The tone function itself configures the output to the pin to an output, so we don't need a separate pin mode function here. The first tone function call has the speaker pin and then a 440 for a 440 hertz pitch. Then there's a delay of a second, which allows the hardware to continue playing that square wave pitch for that duration. The no tone function will turn off the sound and needs the same pin number that you gave to tone. And then that will delay for a second to silence. And then the second tone declaration here, invocation, uses a pitch of 660 hertz for a second. So those are chosen as musical pitches. 440 is the definition of an A4, sometimes called concert A. It's a common orchestral tuning pitch. And in the Western equal temperament, 12-tone temperament scale, it's the only set of precisely valued tones. Everything else has some fractional value. The second pitch here is 660, which is what's known as a perfect fifth using a pure 3/2 ratio, which is a particular intonation called just intonation. It's a common ratio that is used by musicians, especially singers and other instrumental players, who are taught to play that particular tuning for a fifth to get a really lovely open fifth kind of sound against the lower pitch. It doesn't exactly correspond to the piano pitches. It's slightly wider. And the piano fifth is actually slightly inharmonic and it's very slightly jarring. It doesn't quite sound together. And mostly this is to say that there's a variety of different pitch tuning systems, none of which are exactly the same, and each produces a slightly different musical outcome. So every one of these is an approximation. Let's go to the second example now, which takes a very different approach. So bit bang two-tone, and let's just give that a whirl. Now in this case, there is no tone function, so let's just hear what this sounds like. So what we're hearing is the superposition of two sounds along with some artifacting. If you look what's going on in here is that the Arduino program is using digital write to directly create an audio signal by turning the output on and off at a very high rate. So in this case, we are using digital write. We do need a pin mode in the setup to configure that for output. And then if we look at what's happening inside of loop, the loop function is designed to run as fast as possible. And every time that it starts, it reads the microsecond clock, which is a 32-bit number, and stores it into now, this variable. And then it uses a little bit of logic to create two square waves. The microsecond clock, the percent sign is a modulo operator. So it's divided by 2274, and the remainder is the value of the modulo. That's compared against 1136, so that for half of the period, from 0 to 2273, the waveform will be off, and the other half it'll be on. Similarly, for the second square too, there's a different divisor, but the same logic. It creates a square wave of a different pitch. If we look down at the digital write, there's a caret operator, which is a bitwise exclusive OR. This depends upon the fact that the Boolean is actually either a 0 or 1. And so the exclusive OR has the property that it's true when the inputs are different. So a 0 and a 0 produces a 0. A 1 and a 1 produces a 0. But then 0, 1 or 1, 0 produces a 1. It's a way of superimposing two square waves or two digital waveforms to produce a composite signal. Now let's look at these actual divisors. If you take 2274 microseconds and you divide that by 1, or 1 by that, it's reciprocal, then what we see is that the period of that is actually that period produces a 439.75 and some fraction hertz signal. It's not exactly at A4, it's close, but not quite right. And this is mostly a consequence of the fact that we have a fixed 16 megahertz clock that is divided down by integer division hardware to produce some rate. And there's only certain rates that are available. So when you ask the tone function for 440, internally it's doing some approximation to find the closest divisor and then actually producing a pitch that is slightly off. It's just a consequence of having integer-based hardware. Similarly, the second pitch here is very close to that E5 at that perfect fifth above the lower tone. So that's a bit banging approach, and that can be used to generate quite complex waveforms on a real Arduino that has the bandwidth to spare. One thing to note here is that because the microsecond clock is being used, the execution of this loop can vary in time. There can be some jitter, we call it, in terms of variation of time of the loop, and the outcome should be very, very similar. It's using the hardware clock to determine the timing. So even if there's some other operations that might cause the timing to vary slightly, because the hardware is the reference and is being divided down, the actual waveform might have some subtle jitter where the different periods are slightly different from cycle to cycle, but the overall frequency will be very stable and consistent. Let's go to the third example now, which is called scale, and it goes back to using the tone function. So once again, it has tone. Let's just hear what this sounds like. So what we're seeing here is a 2-octave chromatic scale. So let's look at the code. Once again, tone is used. There's no pin mode in setup. Setup is blank. So we have this variable frequency, freq, which is a float variable. And it starts with a value of 440. That's our concert A4. Then we have a loop that will loop 24 times. And on each time, it will generate a pitch on the speaker, delay for 200 milliseconds. And then there's a multiplier, freq equals freq times 1.0595. That's approximately the value of 2 to the 1/12th. That number multiplied by itself 12 times equals 2. And basically this expresses the idea of an equal temperament scale where each semitone is a fixed ratio of the semitone below it, but every 12 semitones is an octave. In musical terms, going from A4 to A5, an octave is a doubling of frequency. So 440 at A4 is 880 at A5. So this performs the arithmetic on each cycle to simply compute the next semitone in the sequence as it walks up that chromatic scale. And then finally it finishes with a no tone to give us a second of silence in between the scales. So in summary, the tone function is useful for causing the hardware to produce a square wave while something else happens. We're not really taking advantage of the fact that the CPU is free. We're just delaying that interval. But we could actually have a lot of other computation happen while that pitch continues to come out. And then we've looked a little bit at these various tuning systems to see that there are different schemes for producing the ratios of pitches that form musical notes. I'm going to walk through some sample code from the course site to talk a little about using functions in Arduino programming. So we look here in the lecture sample code. In the sound section, there's the arpeggio demo. I'm going to copy the code and paste it into a Tinkercad sketch. The circuit just has a speaker wired to pin 5. So let's first give it a quick listen. So not a brilliant composition, but it is something. Let's look at the loop function. And what we see is that we see 6 function calls to both arpeggio and silence. And these are functions or procedures that are defined within this file. They're part of the solution. And we'll also note that the arpeggio function takes 3 parameters that are integers. So let's look at arpeggio and see what's going on. Arpeggio has the parameters start, interval, and length. They're all integers, native 16-bit integers. And essentially, it is looping over a set of note values, going up by a fixed interval for a fixed number of iterations. And on each time, it plays the sound. So a lot of is happening in the for statement on line 27. The first expression, the initializer, we'll see now has 2 different integers being declared, note and count, with initial values of start and 0. So note will be our note index that walks up along the interval, and count will simply count the number of notes that have played. The continuing expression, the predicate in the second position, count is less than length, is what allows the loop to run as long as we haven't played the right number of notes. And then in the third term, which is a little off screen here, there are actually 2 expressions. One is an assignment to increase note by interval to step up during the arpeggio. And the second is an expression to increase count by 1. So that will keep count of each note as it plays. Within the body of the loop, we see a couple things. First is there's another function call, this time to MIDI to freq, given that integer note value. And what it returns is a frequency value as a floating point number, which we store in the temporary variable freq. We print it for debugging and then use that to drive the tone function to generate the sound and then wait while it plays. So a couple things to note here. First of all, we define that function just below. We'll look at that next. Second is it's a floating point return value which we pass to tone. And just a comment that tone accepts an integer value, but when C++ sees a floating point passed into an integer function, it'll automatically add some code to truncate it from float to integer. Let's look now at MIDI to freq. And that is down below here in the same file. There's a couple of constants that drive it. MIDI underscore A0 is equal to 21. Freq A0 is a frequency value of 27.5 hertz. The MIDI system of note values uses integers that correspond essentially to piano keyboard keys, with 60 as middle C, and this is a deep low A note. It's actually sub-audible for most people, 27.5 hertz. So what we see inside the function is a closed form expression for computing an equally tempered scale. Pow is a mathematical function that raises x to the y. In this case, we're raising the constant 2 to n over 12, where n is the number of semitones up along a scale. So for MIDI note here, it's subtracted from MIDI A0 to get an offset, and for the note A0, that would be 0, and the power would just return a 1. For the octave above that, MIDI note would be 21 plus 12 is 33. That would produce a 12 divided by 12 would be a 1. 2 to the 1 is 2. So every octave of musical notes is a doubling of frequency, and then the notes in between, the semitones along the scale, are distributed exponentially between those. So this function is a way of encapsulating that idea and putting it into kind of reusable form, allowing us to sort of get away from the math and think just about the process, like how do you translate a note to a frequency, and then using that idea up above. The silence function doesn't take any parameters and doesn't return any arguments, so it's marked with a void inside the parentheses and a void keyword to the left of the name. And it's simply used to encode the idea of an operation that produces some silence. So there's a couple of different ways that functions are being used here. One is to provide a reusable building block. So the arpeggio function is called 3 times in the loop, each with different parameters. And that allows us to abstract away a little bit from the specific note values to the idea of a process that we can control, and then reuse that as an idea several times. Silence is a little simpler, but also it encapsulates an idea of an action that can then be reused. The MIDI to freak sort of is used as a way of creating a reusable building block, which includes both parameters and return values that maps one number to, or one set of numbers to another number. And it's a way of basically kind of encapsulating an idea that in a way we can then chunk it and not have to think about the details. In both cases, the idea is that in some sense we're creating a very tiny language. This set of expressions inside the loop of arpeggios and silences is a way of encoding our idea about this composition as consisting of 2 different ideas that are then expressed in functions. And that could be taken to arbitrary level. There could be a phrase function that calls, arpeggio a number of times, and a movement function that calls multiple phrase functions. It really is getting to the point of trying to think about your solution to a problem in terms of composable building blocks that then be mapped onto functions in the code. And it saves on code writing, it makes it easier to debug, but also it's a way of trying to map your idea directly into code that makes it easier to think about in terms of that idea. So what we've seen in here is, just to back up, we've seen functions used in a couple ways: functions with parameters and return types, functions used as building blocks, functions used as composable building blocks that we can then reuse over time. And I think all these things are good methods for building up musical compositions on the Arduino. I'd like to discuss a few details of the exercise servo motion in Tinkercad. In my mind, the sort of chief objective here is to explore more programming practice, specifically regarding around organizing sketches in terms of functions. But at the same time, we're going to introduce the hobby servo because it's a very useful item that we will use quite a bit. Tinkercad itself is fairly limited. We can make them move, but we can't actually connect them to a mechanism. So the exercises are limited to kind of just showing a motion. And I provide a sample circuit here. The details of the circuit are not the focus of the exercise, but you do need to wire up a circuit in order to make this go. Just for reference, I'm going to be drawing today from the lecture sample code. Under the servo section, there's the SHM servo sample sketch, and that's what I'm going to be using as an example. But I suggest that you consider other possibilities and think carefully about how to create some structured motion. So I have a sample sketch here, and the essence is that there is a microservo, a hobby microservo. This particular one has a pinout where the power lead is in the center pin. Not all servos have the same pinout, but I'm using a 5 volts from the Arduino to power the servo. And then there's a control signal, the green wire, that is routed from digital output D9. All my examples use D9 just arbitrarily. Any digital output pin should actually work to drive the servos. So just to see this go, I'm going to start the simulation and note a couple of things. First, I have a couple extra voltmeters. There's just one showing the 5 volt supply to guarantee it's 5 volts. And then there's a oscilloscope that is required for you to use as well, which is showing a pulse that's varying in width. This is the command signal to the servo. And this is a format that was invented by the radio control community. And it's a pulse that varies in length between 1 and 2 milliseconds. And it's the length of the pulse that encodes the target angle of the servo in basically a kind of analog way. It's a digital output in that it's a binary output, but it's definitely encoding an analog value. And if we zoom out a little bit, that is showing 5 milliseconds across the scope, or half a millisecond per division. If I update that to look at a longer time scale, I look at 20 milliseconds per division, what we see is a long series of pulses, each varying in width. And this is the standard. Typically, these pulses repeat at a rate of 50 hertz, that's 20 milliseconds apart, and each one encodes an angle. And that determines the sort of basic update rate of the command to the servo. It doesn't help to try to command it faster than that, because the pulses only come out every 20 milliseconds. That basically determines how fast you can try to change the set points. We'll get back to sort of physical hobby servos more once we have kids and are working in physical electronics, but just in summary, it is a kind of a fully closed loop device. There's a position sensor, usually a tiny potentiometer measuring the angle of the output shaft. There is a circuit that is using that as a measurement and comparing against the reference signal that you provide to decide whether to drive the motor forward or backwards. It's typically the motor is mostly running in a kind of saturated mode where it runs at full speed, and then there's a linear region around the target where it will slow down to approach the target, and a very small dead band right at the target to avoid it chattering for tiny errors. And these have all their quirks that we'll understand much better when we get to physical practice. But for now, we can just treat it as a kind of controllable output device where you send in a position command and it moves to the position at some rate. And if you send a series of changing position commands, then it will, by and large, track that path. Although the accuracy of that track depends upon a lot of factors, including the maximum speed you're trying to achieve, the specific servo, kind of the loading, all sorts of other factors. But for now, we'll treat it just as an output device and mostly think about programming. So that is the essence of the circuit. And I do want you to definitely wire in the Arduino, the servo, and the oscilloscope so you can also look at your pulses and sort of explore that pulse train. I'm going to set this back to half a millisecond per division, which is, the oscilloscope's sometimes a little fussy there. There we go. So you can see the individual pulse varying. That's 500 microseconds per division. So let's look a little bit at the rest of the program here. We can see in the serial monitor, there's a series of numbers coming out. Those are the target angles. The servo library on the Arduino takes angles between 0 and 180. And physical servos typically have a kind of 180-degree range of travel, although some can go a little more. It's almost always, most servos that we use will have a fixed travel. They don't rotate continuously. So they're always used in either some kind of angular position mode or with a tie rod to get some kind of like specific linear mode. And then we see a plot here showing a kind of ringing sinusoidal waveform. And that's the detail here of the sketch today. So I'm going to stop the simulation so I can close these windows and look a little bit at the code. I gave this example mostly because it demonstrates that we can get beyond tables and actually write more kind of complicated mathematical functions that produce motion, just because it's a nice technique. It's very physically motivated. In some sense, what this is doing, this simulator, is it's simulating a mass spring system as a second-order differential equation, and then using that as data to drive this physical servo. So it's giving the servo a more fluid kind of motion that's physically motivated, although it's coming from a simulated source. So to kind of get down to the heart of it, let's look at the ringing servo function, which is what's generating the actual movement. It takes 4 parameters, a reference position, which is the center of the oscillation, a stiffness, a damping, and a duration in seconds. So the K and B correspond to the spring constant and the damping constant for the simulated spring and damper. And what we see is the second order differential equation. There's a acceleration that's computed that's QDD, which is the spring constant times the displacement between the current position and the desired position. And then a damping term, B times QD, which is basically applies an acceleration to always in the opposite direction from the velocity to suck mechanical energy out of the oscillation. It's simulated mechanical energy. So in this case, it's all about this virtual mass spring damper system. Then there's an Euler integrator. Takes Q equals Q plus QD times dt. That's basically taking the position and then adding one discrete time step of velocity. And then the same thing for updating the velocity with one discrete time step of acceleration. There are other integration schemes. This is a straightforward one, which for the time scales we're talking about is numerically stable, although it is possible to choose parameters here that will make this go unstable and produce sort of wildly unstable oscillations. The servo.write, svo.write, svo is my servo object. That actually sends the command to the servo, and then I print it for plotting. And then here I'm waiting a duration between the integration steps. And this is also just chosen to match the fact that the servo has a finite update rate. It turns out that integrating the system at 50 Hertz is sufficient to remain stable, and that both delays the real time till approximately the next time that the servo is updated, as well as keeps track of the duration for timing the ring. So a couple other points here. The loop function has just a couple calls to this primitive. I'm calling it a motion primitive because it's a function that generates an entire movement over time, and that's now kind of an action in our language, in our grammar for this movement. For your exercise, I'd like you to think about some other possible sort of phrases here and how you might parameterize other functions or make kind of a phrase structure around some primitives to give a little variety. And effectively, the outcome is a kind of kinetic composition. Before we were doing a melody composition, now it's going to be kind of a moving composition on one motor. And then last, just to get back to the kind of more sort of technical details of using the Arduino, we'll note that at the very top there is an inclusion of servo.h. Servo is not a automatically available library. It's a library that has to be specifically included. This notation is C++ notation for including a header file, which is the standard way that we make the definitions of the library available to your program. So it's an obligatory line to make sure that that library code is available. We declare a const for our servo pin, and then line 7, servo SVO, is declaring a servo object. The servo object is some C++ class, and we're going to create an instance of that class. You can give it whatever name you like. Here I just called it SVO. That's your name that you get to choose. And that just creates this object. And once again, this is kind of using a C++ structure in a way that more or less insulates you from the sort of C++ idioms. And you can pretend that SVO is just a global variable. You do need to initialize it. In the setup function, there's an attach method that's called, which basically configures that pin to use the physical hardware pin. And behind the scenes, this does set up some mechanism inside of the timer interrupt and with the timer hardware on the chip to enable creating this pulse train on that pin. And that is part of the library function. It hooks into the timer interrupt, and it can regularly turn the pin on and then turn it off at a fixed interval later. It's a very flexible library. It can handle many, many servos on one Arduino, and gives you kind of an easy access to a lot of programmed motion. So that's kind of a quick walkthrough of this specific solution to the exercise. The key really is just figure it out, learn how to wire it up, learn how to set up a servo on a pin. Think about program structure, how you might create one or more motion primitives that create some kind of action over time, and then think about how you might create one or more phrase functions that compose those into a motion sequence. And that's kind of the central idea. I'd like to discuss a few details of the exercise servo motion in Tinkercad. In my mind, the sort of chief objective here is to explore more programming practice, specifically regarding around organizing sketches in terms of functions. But at the same time, we're going to introduce the hobby servo because it's a very useful item that we will use quite a bit. Tinkercad itself is fairly limited. We can make them move, but we can't actually connect them to a mechanism. So the exercises are limited to kind of just showing a motion. And I provide a sample circuit here. The details of the circuit are not the focus of the exercise, but you do need to wire up a circuit in order to make this go. Just for reference, I'm going to be drawing today from the lecture sample code. Under the servo section, there's the SHM servo sample sketch, and that's what I'm going to be using as an example. But I suggest that you consider other possibilities and think carefully about how to create some structured motion. So I have a sample sketch here, and the essence is that there is a microservo, a hobby microservo. This particular one has a pinout where the power lead is in the center pin. Not all servos have the same pinout, but I'm using a 5 volts from the Arduino to power the servo. And then there's a control signal, the green wire, that is routed from digital output D9. All my examples use D9 just arbitrarily. Any digital output pin should actually work to drive the servos. So just to see this go, I'm going to start the simulation and note a couple of things. First, I have a couple extra voltmeters. There's just one showing the 5 volt supply to guarantee it's 5 volts. And then there's a oscilloscope that is required for you to use as well, which is showing a pulse that's varying in width. This is the command signal to the servo. And this is a format that was invented by the radio control community, and it's a pulse that varies in length between 1 and 2 milliseconds. And it's the length of the pulse that encodes the target angle of the servo in basically a kind of analog way. It's a digital output in that it's a binary output, but it's definitely encoding an analog value. And if we zoom out a little bit, that is showing 5 milliseconds across the scope, or half a millisecond per division. If I update that to look at a longer time scale, I look at 20 milliseconds per division, what we see is a long series of pulses, each varying in width. And this is the standard. Typically, these pulses repeat at a rate of 50 hertz, that's 20 milliseconds apart, and each one encodes an angle. And that determines the sort of basic update rate of the command to the servo. It doesn't help to try to command it faster than that, because the pulses only come out every 20 milliseconds. That basically determines how fast you can try to change the set points. We'll get back to sort of physical hobby servos more once we have kids and are working in physical electronics, but just in summary, it is a kind of a fully closed loop device. There's a position sensor, usually a tiny potentiometer measuring the angle of the output shaft. There is a circuit that is using that as a measurement and comparing against the reference signal that you provide to decide whether to drive the motor forward or backwards. Typically the motor is mostly running in a kind of saturated mode where it runs at full speed, and then there's a linear region around the target where it will slow down to approach the target, and a very small dead band right at the target to avoid it chattering for tiny errors. And these have all their quirks that we'll understand much better when we get to physical practice. But for now, we can just treat it as a kind of controllable output device where you send in a position command and it moves to the position at some rate. And if you send a series of changing position commands, then it will, by and large, track that path. Although the accuracy of that track depends upon a lot of factors, including the maximum speed you're trying to achieve, the specific servo, kind of the loading, all sorts of other factors. But for now, we'll treat it just as an output device and mostly think about programming. So that is the essence of the circuit. And I do want you to definitely wire in the Arduino, the servo, and the oscilloscope so you can also look at your pulses and sort of explore that pulse train. I'm going to set this back to half a millisecond per division, which is, the oscilloscope's sometimes a little fussy there. There we go. So you can see the individual pulse varying. That's 500 microseconds per division. So let's look a little bit at the rest of the program here. We can see in the serial monitor, there's a series of numbers coming out. Those are the target angles. The servo library on the Arduino takes angles between 0 and 180. And physical servos typically have a kind of 180-degree range of travel, although some can go a little more. It's almost always, most servos that we use will have a fixed travel. They don't rotate continuously. So they're always used in either some kind of angular position mode or with a tie rod to get some kind of like specific linear mode. And then we see a plot here showing a kind of ringing sinusoidal waveform. And that's the detail here of the sketch today. So I'm going to stop the simulation so I can close these windows and look a little bit at the code. I gave this example mostly because it demonstrates that we can get beyond tables and actually write more kind of complicated mathematical functions that produce motion, just because it's a nice technique. It's very physically motivated. In some sense, what this is doing, this simulator, is it's simulating a mass spring system as a second-order differential equation, and then using that as data to drive this physical servo. So it's giving the servo a more fluid kind of motion that's physically motivated, although it's coming from a simulated source. So to kind of get down to the heart of it, let's look at the ringing servo function, which is what's generating the actual movement. It takes 4 parameters, a reference position, which is the center of the oscillation, a stiffness, a damping, and a duration in seconds. So the K and B correspond to the spring constant and the damping constant for the simulated spring and damper. And what we see is the second order differential equation. There's a acceleration that's computed that's QDD, which is the spring constant times the displacement between the current position and the desired position. And then a damping term, B times QD, which is basically applies an acceleration to always in the opposite direction from the velocity to suck mechanical energy out of the oscillation. It's simulated mechanical energy. So in this case, it's all about this virtual mass spring damper system. Then there's an Euler integrator. Takes Q equals Q plus QD times dt. That's basically taking the position and then adding one discrete time step of velocity. And then the same thing for updating the velocity with one discrete time step of acceleration. There are other integration schemes. This is a straightforward one, which for the time scales we're talking about is numerically stable, Although it is possible to choose parameters here that will make this go unstable and produce sort of wildly unstable oscillations. The servo.write, svo.write, svo is my servo object. That actually sends the command to the servo, and then I print it for plotting. And then here I'm waiting a duration between the integration steps. And this is also just chosen to match the fact that the servo has a finite update rate. It turns out that integrating the system at 50 Hertz is sufficient to remain stable, and that both delays the real time till the next, approximately the next time that the servo is updated, as well as keeps track of the duration for timing the ring. So a couple other points here. The loop function has just a couple calls to this primitive. I'm calling it a motion primitive because it's a function that generates an entire movement over time, and that's now kind of an action in our language, in our grammar for this movement. For your exercise, I'd like you to think about some other possible sort of phrases here and how you might parameterize other functions or make kind of a phrase structure around some primitives to give a little variety. And effectively, the outcome is a kind of kinetic composition. Before we were doing a melody composition, now it's going to be kind of a moving composition on one motor. And then last, just to get back to the kind of more sort of technical details of using the Arduino, we'll note that at the very top there is an inclusion of servo.h. Servo is not a automatically available library. It's a library that has to be specifically included. This notation is C++ notation for including a header file, which is the standard way that we make the definitions of the library available to your program. So it's an obligatory line to make sure that that library code is available. We declare a const for our servo pin, and then line 7, servo svo, is declaring a servo object. The servo object is some C++ class, and we're going to create an instance of that class. You can give it whatever name you like. Here I just called it SVO. That's your name that you get to choose. And that just creates this object. And once again, this is kind of using a C++ structure in a way that more or less insulates you from the sort of C++ idioms. And you can pretend that SVO is just a global variable. You do need to initialize it. In the setup function, there's an attach method that's called, which basically configures that pin to use the physical hardware pin. And behind the scenes, this does set up some mechanism inside of the timer interrupt and with the timer hardware on the chip to enable creating this pulse train on that pin. And that is part of the library function. It hooks into the timer interrupt, and it can regularly turn the pin on and then turn it off at a fixed interval later. It's a very flexible library. It can handle many, many servos on one Arduino, and gives you kind of an easy access to a lot of programmed motion. So that's kind of a quick walkthrough of this specific solution to the exercise. The key really is just figure it out, learn how to wire it up, learn how to set up a servo on a pin. Think about program structure, how you might create one or more motion primitives that create some kind of action over time, and then think about how you might create one or more phrase functions that compose those into a motion sequence. And that's kind of the central idea.